Hi, this is Math 6. Let me share the screen. We're going to learn lesson 5-4, representing and graphing ratios. In this lesson, we'll be able to solve ratio problems by using tables and graphs to show equivalent ratios. Let's look at solve and discuss it. For every 4 adults at the beach one afternoon, there were 3 children. How many children were at the beach if there were 8, 12, 16, or 12 adults at the beach? So we have a ratio. We can make a table of equivalent ratios. The number of adults, 4 adults at the beach, and there were 3 children. If the ratio is constant, which means it's the same, you can make an equivalent ratio to get 8, 12, 16, and 12 adults at the beach. 8, 12, 16, and 20. So go ahead and write the numbers down for the adults. This is number of adults. So 4 times 2 is 8. So you multiply 3 by 2. 4 times 3 is 12. So you multiply 3 times 3. 9. 4 times 4 is 16. 3 times 4 is 12. 4 times 5 is 20. 3 times 5 is 15. And that's how you can generate a table of equivalent ratios. Okay. How does the graph show the ratio? Can we graph them? Ooh. Do you remember how to graph? If you have points, if you have two variables that have a relationship and they're proportional, you can graph them too. So look at the x-axis. X-axis represents the number of adults. Y-axis represents the number of children. So look how many adults you have for every children. 4 adults by 3 children. So let's put that point. If you have 4 adults, you have 3 children. 3 should be about here, right? So 4, 3 is right here. And what about 8 and 6? If you have 8 adults, you have 6 children. So dot, 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 dot here. Dot, 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 dot here. Yeah? So that's 8, 6. And then you're gonna keep making the graph, making the points, plotting the points using the table. 12, 9, 16, 12, 20, 15. 12, 9 should be here. And then 12. Okay. And then 16. Yes. 16, 12. And then 20, 15. 15 is right here. And 20 is here. Okay. So that's 20, 15, 16, 12, 12, 9. Okay. And those are the points that you can graph on the coordinate grid. And if you connect the points, you can draw a nice little line. Okay. So how does the graph show the ratio? The points on the line represent what? The equivalent ratios of what? 4 adults to 3 children. Okay. All right, focus on math practices. There were 25 children and 15 adults at the beach. Anne-Marie said that there were 5 children for every 3 adults. Is he correct? Okay, so 25 to 20. So basically, is 25 to 15 adults the same equivalent ratio with 5 children to 3 adults? Are they equivalent ratio? Well, let's see if they can be divided with the same number. 25 divided by 5 is 5. Okay, is 15 divided by 5 3? Yes. So yes, they're equivalent ratios. Okay, 25 divided by 5 is 5, and 15 divided by 5 is 3. So 25 and 25 over 15 is equal to 15 over 3. They're equivalent ratios. All right, so in this lesson, we will think about how we can use tables and graphs to show equivalent ratios. Example 1, explore ratios in tables and graphs. Ellen is shipping for supplies at Jake's party store. Make a table to show how much Ellen would spend to buy 3, 6, 9, or 12 balloons. Then plot the pairs of values in a coordinate graph and use the graph to find the cost of 18 balloons. So Jake's party store, balloons 3 for $2, hats 5 for $3, streamers 4 for $1. How can you make a table of equivalent ratios or a graph to find the cost for other numbers of balloons? So you can make a table with the number of balloons versus cost in dollars, right? We got balloons 3 for $2. So 3 over 2. And then make equivalent ratios. You can also plot that on the graph. 3, 2, 6, 4, 9, 6, 12, 8, and so on. And so you can figure out the point 18, 12 is on the line. And so that shows the cost of 18 balloons. So the cost of 18 balloons would be 12. You need to know which, in this point, 18, 12, which represents which. 18 represents the X value, X, Y, right? X represents the number of balloons. So that's number of balloons. And Y represents the cost in dollars. So 12, for 18 balloons, it costs $12 is what you are trying to get. Example, try it. What are the coordinates of the point that represents the number of balloons you can buy for $6? So you want to look at the Y value first, $6, and then see how many balloons you have for that one. 6, comma. On this graph, it's easy to just pick a point, right? You can see that this is at 9, 6, 9. Right? Wait, that's 9, 6. I'm sorry, I switched. That's 9, 6, but you can find 6 first on the graph and see what X value would correspond to that values of Y, which is 9. So you have 9 balloons for $6. Okay. So they're just asking the coordinate, which is X, Y, the point. So you can just write 9, 6. Convince me, how can you use the graph to find the cost of 15 balloons? What do you do first? Don't just find the cost of 15 balloons. Like, explain, how do you use the graph? Find 15 on the X or Y axis. It's balloons, so balloons is on X-axis. On the X-axis, then find the corresponding Y value on the line. So then 15 balloons, if you have 15 balloons, how much would it cost? It will cost $10. 15 balloons will cost $10. Okay, that was example 1. Let's look at example 2. Graph ratios using repeated addition. Jack is making juice. He has 25 celery sticks. If Jack uses all 25 celery sticks, how many apples will he need to make the juice? You're gonna find the ratio. We got apple celery juice recipe here. 5 celery sticks with 2 apples. So that's our ratio. 5 celery sticks to 2 apples. And so you're gonna make a table using equivalent ratios. If you add 2 for apples, you need to add 5. So you can use addition to make equivalent ratios, but you're going to add different values. Every time you add 2 for apples, because that's where you started, you're going to add 5 for celery. Or you can just multiply the same number to both of them. Okay. So, but this also explains how the graph has a slope. You can count the slope as well. You go 5 to the right and then go up 2. But it happens that this 2 squares is 2 for y value and 2 squares would be 5 for y value. So it looks very even, but actually you're going 5 blocks, 5 units to the right, 2 units above to count the slope for the graph. Okay, that's how you can graph using counting. Example 3, graphing ratios related to pi. Remember how we figured out the ratio of pi, like the equivalent ratios of pi in the last lesson? We have more of these. The measurements of different circular objects are given in a ratio table. What do you notice about the graph of the pairs of values given in the ratio table? Okay, we have a ratio table here. Fruit plate in diameter is 7 inches and circumference is 22 inches. Clock face, this one, has diameter of 14 inches. Diameter would be radius times 2. So that's 14 inches. Circumference is the whole length around the circle, 44 inches. And then hula hoop is going to have 35 inches. And then the whole circumference is 110 inches. Do we have a relationship between the diameter and the circumference is what we're gonna look at. So we have a graph of x-axis being the diameter d and y-axis being the circumference c. We can make a table of values, 7, 22, 14, 44, 35, 110, and see if the points would make a straight line. The graph of the values in the ratio are on the same line, in a straight line. So we can say that they have a proportional relationship, okay? So whenever you see a straight line on the graph, after you plot all those points, that's when they have a proportional relationship and they have equivalent ratios. Let's look at try it. Can you draw an object with a diameter of 10 inches and a circumference of 50 inches? If you can, explain. So first, we need to see if it's proportional. Diameter 10 inches. So if you know the circumference equation, circumference is what? 2 pi r. So, so the ratio of circumference and the radius, 2r is actually the diameter. So it could be d pi. So pi is really c over circumference over diameter. Okay, and that's what we have here in the table, in the graph. Okay, that's the ratio we should have. But is diameter 10 divided by circumference 50 inches divided by 10 pi. Well, no, 50 divided by 10 is going to be 5, and that's not even close to pi. Pi should be about 3.14. But how can we prove this using the equivalent ratio that we looked at in example 3? Okay, let's look at diameter 10 over here. So if that's 50, that's 25, 10 would be around here. What about circumference of 50? 50 is about here. So 50 should have a circumference of about 25 or 24, you know, but close to 20 something, right? But 10 is not even close. Okay, 10, 50 is over here, and it is not on the line. So you can say the ratio is not equivalent using the graph. Okay, so no, 10, 50 is not on the line. Even though it's very close, if you zoom in into the graph, it's not even close. It's not on the line. If it's not on the line, it is not equivalent. Okay. So it's not equivalent to pi. All right, that was our lesson 4, representing and graphing ratios. In this lesson, we learned how to graph the ratios using our tables of equivalent ratios. Just make sure you know which axis represents which variable. All right, that was lesson 4. We'll continue with the next lesson in the next video. Thanks for watching. See you later.